Okay, so dear participant, we can start our seminar. Our speaker Yunfeng Jiang from Southeast University. Which town?
Nanjing.
Nanjing. Yes, he will speak us about spin S rational Q systems. Let us start your talk.
Okay, thank you very much. So first, I would like to thank the organizers of this seminar series for the very kind invitation. And it's really a great pleasure to talk in front of a group of integrability experts so that I don't need to explain what is the Bethe ansatz. So the topic today is slightly technical, but I think it should be interesting for integrability guys. So it's about a rational Q system for the spin S, XXX spin chain. So this is mainly about solving Bethe equations of the XXX spin chain for spin S. So this talk is based on the recent work which appeared on Archive in March in collaboration with Hou Jue, who is my postdoc, and Ruidong Zhu from Suzhou University. Okay, so in the first part, I'm going to first explain what is the rational Q system and also explain its relation to the completeness problem for the Heisenberg spin chain, for the Bethe ansatz of Heisenberg spin chain. So this will mainly be about spin half, because after this rather detailed explanation for the spin half situation, we can better appreciate what is new and what has been done in the spin S case. So let me get started. First, there are some fundamental things. So our interest is the Heisenberg spin chain. This is the Heisenberg spin chain. Well, when you take delta equals 1 is the XXX spin chain. So when delta is not 1, then this is the XXS spin chain. So the main task for physicists is to find the eigenvectors and the eigenvalues of this Hamiltonian. And it's well known that the Heisenberg spin chain can be diagonalized by Bethe ansatz. So each beta state can be constructed by either coordinate Bethe ansatz or algebraic Bethe ansatz, and each beta state is parameterized by m parameters, which we call beta roots. So these beta roots have to satisfy a set of equations called Bethe ansatz equations. And here in this talk, I will mainly consider the XXX spin chain. So the Bethe ansatz equations takes this rational form. This is the form of the Bethe equation. Now about Bethe ansatz, there's a fundamental problem, which is the completeness problem. So roughly speaking, the completeness problem is the following, which is, does Bethe ansatz give all energy eigenstates? So we know that Bethe ansatz is a certain kind of ansatz. It gives you some eigenstates, but does it give all the eigenstates? So is there any eigenstate that doesn't take the form of Bethe ansatz? So this is this kind of question that is the completeness problem. So this problem was posed actually at the very beginning of Bethe ansatz. And after many years of study, now I think we understand that for the spin 1/2 XXX spin chain, the answer is yes. And this has been studied for many, many years and for different models. And there's a very rich structure here. So why this is an interesting and difficult problem? So I think there are at least two difficulties. So the first difficulty is that not all the solutions of Bethe ansatz equations, which I just showed you, correspond to energy eigenstates. Namely, there are some solutions which are not physical. They do not correspond to eigenstates, and they should be thrown away. So if this is the case, we need to understand when does this happen? Namely, when are the solutions not good? And second, how can we select the good physical solutions? So this is the main one of the main difficulties. And the second difficulty is that now after you throw out these bad solutions, can you count the number of the good solutions? Namely, how to count the number of solutions of Bethe-ansatz equations. So this is also a non-trivial question because the Bethe-ansatz equation is a set of nonlinear system of algebraic equations. And there's no, there's a typo, there's no analytic solution in general. And also the complexity of this equation just grows quickly with the quantum number. So this is also a difficult task. So let me start to discuss the main difficulty one, namely when do we have problematic solutions? So for the XXX spin chain, there are two types of Bethe solutions that we need special care. So the first type of solution are the Bethe solutions which include repeated roots. So the solution with repeated roots takes this form. You have two or more rapidities which are the same and the rest are different. Let's say we have this form. So if you take such a solution and if you plug in the coordinate Bethe-ansatz wave function, you find that the beta vector is identically 0. So this is just because the special normalization in the coordinate Bethe-ansatz. We can also plug into the algebraic Bethe-ansatz. In this case, you will find that the beta vector is actually finite, but it does not give an eigenstate. So this is a very interesting fact. So why is this so? Let's analyze a very simple case. So we can consider a 2-magnum state using the algebraic Bethe-ansatz. So these are the usual B operators acting on the pseudo vacuum. Now you want this state to diagonalize the transfer matrix. So when you act the transfer matrix on the 2-magnum state, you will generate two types of terms. In the first line, you have the so-called wanted terms. And in the second and third line, these are the so-called unwanted terms. So if you want this state to be an eigenstate, then you need to put these unwanted terms to 0. So this gives you two conditions, m1u equals to 0 and m2u equals to 0. So these two conditions are precisely the Bethe-ansatz equations for u1 and u2. Now let's consider the case where u1 and u2 are the same, namely you have two u1s. Now again, in this case, you will have the wanted term and unwanted term. So the second line is the unwanted term that we have seen before. But then in the third line, you have a new type of unwanted term because there's a term which involves b prime, which is the derivative with respect to the parameter u, spectral parameter u for the B operator. Now, this gives an extra condition for the rapidity u1. So we see that compared to the one without repeated roots, namely if u1 and u2 are different, then we have two variables and we have two equations. Now, in the case of repeated roots, we have one beta equation, we have one variable, which is u1, but we still have two equations. One is the Bethe-ansatz equation, the usual Bethe-ansatz equation, but there's an additional constraint for u1. So, so this is something we need to keep in mind. Even the number of variables are reducing, but then we still have the same number of equations. So this becomes an overdeterminant system. And in the general case, if k out of the m beta roots, namely if here we have k beta roots are the same, then we have m minus k beta roots for the remaining equations for the remaining beta roots, and we have k constraints for the repeated root, like we just have seen before. So now the question is, so what does this additional constraints look like? To answer this question, it's useful to first consider the eigenvalue of the transfer matrix. So the eigenvalue of the transfer matrix, which is the coefficient in front of the wanted term, takes this form, where this A and D are given here for the XX X spin chain. So the Q is the usual Baxter's Q polynomial. And we'll see that the additional constraints for the repeated roots can be written very compactly using this tau u, which is the following. Now, suppose we have k roots, which we call u0, are repeated, and then the rest are not repeated. Then the additional constraint for u0 just takes this form. So you have 0, you have this L, you need to take derivatives L times, and then you put this u equals to u0, and you require this to be 0. So this, because L runs from 0 to k minus 1, so you have actually k constraints for this one rapidity u0, okay? And we can see easily that this requirement, namely this additional constraint, together with the usual beta roots, beta equations, it is nothing but equivalent to the requirement that this tau u is a polynomial in U. So this is an important observation. And this means that if you want to consider the repeated roots, it's more convenient to consider the TQ relation, just to require T to be a polynomial. And so this is what we do. We can try to solve this equation by requiring that T is a polynomial, this tau u is a polynomial. And we find that in the spin 1/2 case, that the beta-ansatz equation is not compatible with additional constraints. Namely, we cannot find repeated roots for the spin 1/2 case. So I want to emphasize that this fact is rather a numerical observation. So there's a lot of evidence that we don't have repeated roots, but at least as far as I know, maybe I was wrong, there's no proof yet. So I hope that if there are experts in the audience, maybe if you know the proof, please let me know. So I only know that for the Lieb-Lininger model, this has a proof. And the proof was given in a paper by Izergin and Korepin in 1982, but for XXX, so we still lack this proof. But the fact that we accept is that there seems to be no solutions with repeated roots for the spin 1/2 case. Okay, so as I said before, this means if we want to take into account the repeated root solution, we can just consider Baxter's TQ relation, which takes this form. So this might look like a simple rewriting of this eigenvalue of the transfer matrix, but actually we can solve this equation by this form, by making an polynomial ansatz for both tau u and qu. So you can assume that tau u is a polynomial of order L, and the qu is also a polynomial of n. And then you can plug tau u and qu in this TQ relation, and you compare the coefficient of u on both sides. In this way, you obtain a set of algebraic equations for the coefficients tk and cj. And then you can solve these polynomial equations, and you find the solutions directly. So if we compare this approach to solving beta-ansatz equation directly, we find that it's more efficient than solving the beta equation. And also the solutions with repeated beta roots are automatically eliminated. This means if you plug in, say, the beta-ansatz equation directly in Mathematica, it will definitely give you many solutions with repeated roots. But if instead you just solve this TQ relation, you don't find these repeated roots in the spin 1/2 case. So this is the first type of special solutions that we need to be care of. Now, the second type of solution is the so-called singular solutions. So what are these singular solutions? It's the kind of solution which involves an exact two-string. Namely, it has the solution I divided by 2 and minus I divided by 2, and then other regular solutions. So why it is called singular? Because if you plug this solution to the energy formula, namely you can compute the energy using this formula, you'll find that this is divergent if sum of the u's equals plus minus I divided by 2. So if it's divergent, then what should I do? Now, as usual in physics, when there's divergence, we need to do regularization. And it turns out that this regularization is somewhat subtle. So this was done very carefully in a paper by Nepomniachtchi and Wang in 2013. So what they found is that to get the correct eigenvalues, namely the correct eigenvalue of the Hamiltonian, you can do a very naive regularization. Namely, you just shift both U1 and U2 by the epsilon, and then plug in this formula and then take epsilon to 0. Then you will get the correct energy eigenvalue. But if you want to get the correct eigenstates, this is more difficult. You will need a more sophisticated regularization. And you need to add some extra terms, C times epsilon to the power of L. And only in this way, you need to fix C later on. And in this way, you can get the correct eigenstate. So they actually perform this calculation and compare with a direct diagonalization and confirm that their proposal is good. So anyway, by this way of regularization, by this careful regularization, these authors found the following, that what they found is that among these singular solutions, some of them are physical, namely some of them lead to a physical eigenvalue and eigenstates, but some of them are not. So when they lead to physical solutions, this is the actual condition given here. This is what we call the physicality condition. So the conclusion is that if you have singular solutions, then you need to check the regular part, namely the U3 to UN, must satisfy this additional constraint. Then the solution is physical. Otherwise, it's not. And based on these two, based on this observation, they can count how many solutions and how many physical solutions they have, and then they can check the completeness numerically at least. So here I want to mention there's a more rigorous way, a mathematically rigorous way to prove this completeness. And this is based on a very important insight, which is the following.
Excuse me.
So we have seen, yes.
Excuse me, could you say once again, what is the physical condition in more general situation with several pairs of complex roots?
You mean this I divided by 2? There are more times I divided by 2?
Is there some more general definition of the physical condition?
General, in which sense?
In physical sense.
It just means that if you if the rest of this beta roots satisfy this condition, then by using Nepomniachtchi's regularization, you can generate the good eigenstate. Otherwise, if they don't satisfy this, you don't get the good physical eigenstates.
What does it mean, good?
Good just means is the eigenstate of the Hamiltonian. If you plug this solution in the beta state, and then after all this regularization, it is an eigenstate, then it's good. If it's not, then it's not good.
Okay.
Yeah.
Okay. So.
Okay. Okay, thanks for the question. Yes, so we want to understand better what this condition is related to. And an important insight, which I think is based on several works together, is the following. So this physicality condition, which I just explained a little bit, is equivalent to the polynomiality of the dual solution of the TQ relation. So let me explain this point in more detail. So if we go back to the TQ relation, which takes this form, we assume that tau u and qu are polynomials. Now you can regard this equation as a second order difference equation for the polynomial q, for the function qu. And then if this is a second order difference equation, we know that there exist dual solutions. So namely, there are also another solution pu that satisfy the same equation. And this pu and qu, they satisfy the Wronskian relation. So here I just introduced the notation p plus minus is the pu shifted by plus minus I divided by 2, and the same for q. So there's a dual solution, and this is important. So we have assumed tau u and pu are polynomials. However, even if you assume that tau u and pu are polynomials, pu in general is not a polynomial. So this is the crucial part. And there's this following important theorem. Actually, it's proven in 2 papers. So the first part is proven in a paper by Pronko and Stroganov in 1999. This says, if the zeros of qu do not contain plus minus I divided by 2, namely if this solution is not a singular solution, then pu is a polynomial. Actually, they can construct this pu and check that it satisfies the Wronskian relation. Now, the second part, which takes into account the fact that sometimes qu do contain plus minus I divided by 2. And in this case, we have the singular solutions. And in this case, this qu will take this form. So then in the paper of, Gonnet and Jacobsen in 2020, they proved that in this case, when the root of qu correspond to singular solution, then this pu, the dual solution, in general takes this form. So where p0 is a polynomial, but we have psi, which is the digamma function. So this part is not a polynomial. Alpha 0 is an arbitrary constant. And they also show that alpha equals to 0 if and only if this uj, where j runs from 3 to n, satisfies this additional constraint. So from this theorem, we see that this requirement, which is also the physicality requirement by carefully regularizing the beta state, is equivalent to requiring that the dual solution of the TQ relation is a polynomial. So this is a very important insight to understand the rational Q system. Okay, so then if we assume that both solutions of the TQ relation are polynomials, namely now we just focus on the case where both PU and QU are polynomials, then there's this very nice paper by Mukin, Tarasov, and Verchenko in 2009. They proved that if you assume that both PU and QU are polynomials, then all the solutions to this TQ relation are physical. Namely, they correspond to the correct eigenstates of the transfer matrix. And they can even count the number of solutions. And they found the solution is given by this number. So for length L and M magnons, the number is this one. And this is precisely the number of solutions required by completeness. So this number just counts the primary states, because XXX is the SU2 invariant. So you have descendant states of SU2. And this gives you the number of primary states. After you taking into account all the descendant state, you get the correct number, the exact dimension of the Hilbert space. So in this sense, we conclude that Bethe ansatz is complete. So you see, this is really combines several different kinds of works together. We have a full picture of the completeness of Bethe ansatz problem, of the Bethe ansatz completeness problem. So now the question is, can we have a method which eliminates all unphysical solutions? So I know that Bethe ansatz is complete. I can get all the eigenstates in this way. And I know what kind of solutions are not good, but then is there some better method or smarter method which allows me to just get the physical solutions? I don't want the unphysical junks. So is there such a method? And the answer is yes. And this approach is called the rational Q-system approach. And it was proposed by Malboy and Volin in 2016. Actually, when they proposed this, they didn't, there was not a full understanding why Q-system works. People just found that you solve it, it's efficient, it's nice, it gives only the physical solutions. But the mechanism behind was not fully understood. It was only after a few years that people understood why it works. And it's related to what we have discussed so far. But anyway, let me first just introduce to you what is the rational Q system. To construct a rational Q system, we first start with a Yang tableau. And for a spin chain of length L and M magnons, this Yang tableau has two rows. The first row has M boxes, which is the N is the number of magnons. And the second row has L minus M boxes. So the total number of boxes is L, which is the length of the spin chain. Now at each side, we associate a Q function, which we denote by QAS, where A and S are the coordinates on the lattice. Now at each box, whose left lower corner is at coordinate AS, it satisfies the QQ relation. So this means we can associate each point or each node on the Yang tableau a Q, but not all these Q are independent. So the Q functions are related by the QQ relations. And these are the QQ relations. And again, this plus minus means plus minus U shifted by plus minus I divided by 2. So then we impose the boundary conditions for Q. So what we are going to do is that we will fix some boundary conditions and then we will solve for all these Q functions. So the upper boundary are trivial, namely we put all these Q functions to be just one, a constant. And the left boundary, we have two nodes. One is Q00, which is the Q function at the origin, and we fix it to be U to the power of L. And the other one is this Q10, and this we fix it to be the usual Baxter's Q polynomial. And the zeros of Q10 are the beta roots that we are looking for. So how do we see that from the Q system, we can obtain the beta-ansatz equation? So for this, we just focus on the first column. So these two boxes, and we have two QQ relations. The first QQ relation is simpler because we have put two Q functions to one. So it looks simpler. And then there's this second QQ relation. And as we said before, the zero of Q10 is just the beta roots. So we take U equals to UK, namely one of the zeros of Q10, and then we obtain this equation. And we still have some Q11 around. And then we use the first equation. We can shift the spectral parameter U and then put U equals to UK. So this gives us two equations involving UK. And combining these two equations together, we get exactly the beta-ansatz equation. So this tells us that, in fact, the beta-ansatz equations are actually encoded in the Q system. So the solution of Q system will give the solution of beta-ansatz equations. And now, what is the steps to solve the Q system? So we already fixed the boundary Qs in the upper boundary and the left boundary. So then we parameterize the Q10, which we said we want to find its zeros because its zeros correspond to the beta roots. So we parameterize it as a polynomial with some parameter Cj. And then we first solve the first row using the QQ relation. So we find that first row can be solved very easily, where this D is the difference operator. And then we solve the second row. And the key requirement for solving the Q system is that we require every Q function on the lattice is a polynomial. So this is the key requirement. We want all the Q functions on this Young tableau polynomials. So the first row, for the first row, this is trivially satisfied because it's just solved by taking this difference, by acting on this difference operator. And since Q10 is a polynomial, then this is automatically a polynomial. So the first row is always a polynomial. But to solve the second row, we need to do a polynomial division. And there's no guarantee that this division will give you polynomials. So for all the Q0s to be polynomial, we need to require that the remainder of this quotient has to vanish. And this is called a zero remainder condition. And the zero remainder condition actually gives you a set of algebraic equations for the coefficient Cj. So what is this Cj? Cj is here, what I use to parameterize my Q10. Okay. So then instead of solving Bethe equations, we solve this set of zero remainder conditions. And by solving these zero remainder conditions, I can find different solutions of Cj. And then I can plug in here to find my Q10. And after I find my Q10, I can just find its zeros of this polynomial. Then I get the beta roots. And you will see that this procedure, although the description of this procedure is somewhat complicated, but it's not so hard to implement. And it is by far the most efficient way to solve Bethe equations for finite system. And it gives you only the physical solutions. There are no repeated roots. There are no singular non-physical solutions. So only the physical ones. So the question is, why does rational Q system work? So how it is able to do this? And to realize that, to explain this, let me first explain there's this minimality condition. So although we require all the Q functions on the Young tableau are polynomials, in fact, only the first two columns are needed. Because if the first two columns are the Q functions on this shaded part are polynomials, then the rest are polynomials automatically. So it means that the rational Q system actually has certain redundancy. And the minimality condition is that you need to require these guys on this side to be polynomials. The rest are just redundant. So in fact, we'll see that the rational Q system is just a smart way to impose polynomiality. So what does this mean? Actually, we can prove that the first box here, the QQ relation related to the first box here, is actually equivalent to the TQ relation. So, and this TQ relation actually imposes extra condition automatically for the repeated roots. And the second box is actually equivalent to the polynomiality of PU, which is a dual solution. So this imposes some extra conditions for the singular roots automatically. And these two are the minimality conditions for the Q system. So actually this means the Q system really just encodes the polynomiality of tau, Q, and P. So that's why the Q system works. The reason it works is guaranteed by this theorem by Mukin, Tarasov, and Verchenko. So now let me summarize the situation in the spin 1/2 case, which is the following. We start with the beta ansatz equations. So we find there are two kinds of roots we need to be careful. One is the repeated roots. Now the repeated roots has to satisfy, if you have repeated roots, they need to satisfy some additional constraint. And this additional constraint is equivalent to the polynomiality of tau and Q in the TQ relation. And after that, we also need to be careful about singular solutions. And the singular solutions, the physical singular solutions, actually are selected by requiring the dual solution P is a polynomial. So we have this polynomiality of P, and the Q system just encodes both constraints in a nice way, and it gives you only the physical solutions. And that's why rational Q system is very nice, because it gives you the physical solutions and it's very efficient to solve. So this ends my discussion on the spin 1/2 case. So I will pause a bit and see if there are some questions.
Yes.
Yes.
Is this Q system is the same as such appeared in the cluster algebras?
So it's different. That's why I call it a rational Q system. So the QQ relation, I believe, is the same. But basically, this is a tool to solve Bethe equations. So it was developed in 2016, but the usual Q system that related to Hirota and all those business is developed much earlier. So it's similar, but it's not the same.
Okay, thank you.
Okay, so then let me go to the spin S case. So for spin S case, we also have spin S Heisenberg spin chains. So here I give you the spin 1 Hamiltonian. So instead of this, in addition to this quadratic term, you also have this quadratic term. And if the spin increases, the Hamiltonian will become more and more complicated. But for any spin, we can always write down the Hamiltonian explicitly. So such model exists for any spin S. And the corresponding Bethe equation actually is very similar to the spin 1/2 case. All you need to do is to change here this I divided by 2 by I times S.
Sorry.
And the right hand side.
When you write, Sj times Sj plus 1 squared, what do you mean? It's proportional. I mean, it's almost permutation. I mean, permutation square equal to 1.
Yeah. Okay. Let me see. Is it? No, it's not precisely permutation, right?
No, it's permutation minus 1/2, of course. Yeah, but
yes.
if you take 1,
so that's
you have 1
square,
plus
yes.
the same term. Yeah, but I'm not sure that's correct answer. Because this combination is a square, it's up to the constant, it's the first term.
Yeah, I guess you can write it if you want. You can write in other forms, say using permutation operators. But yeah, there's a general formula even from the Fadeyev's review. So it's just it is. Yeah.
Sorry for it, but I'm sure it's wrong formula. But
okay. Thanks. So it turns out this kind of Hamiltonians, you can also diagonalize it by Bethe ansatz.
I'm sorry. Sorry.
Yes.
It's amazing formula. I make mistake. You're right. Thank you. Sorry.
No problem. Okay. So now the Bethe equation actually takes a very similar form. The right-hand side is the same as the spin 1/2 case, and the left-hand side you just change 1/2 by S. And there's also a corresponding TQ relation. Again, it's very similar. You just change this U plus I divided by 2 by U plus IS to the power of L. So it seems rather harmless, right? It seems, okay, then the situation should be more or less the same as the spin 1/2 case. So we want to ask, so in this case, what is new? Well, it turns out the change is quite a bit. So first of all, as we said before, in the spin 1/2 case, we need to be careful about repeated roots and singular roots. Now, the repeated roots are not allowed in the spin 1/2 case, which we found numerically, and there's a lot of evidence. Now, in the higher spin case, you find that repeated roots are actually allowed. So they are part of the spectrum. For example, if you take spin 1, length 8, and the 4 magnons, you'll find this solution where you have 2 zeros. So there are repeated roots. And this is called the strange roots by Nepomniachtchi and collaborators. So they're repeated, but they're physical. So this is one of the crucial difference between the high spin case and the spin 1/2 case. And then, okay, apart from the repeated roots, which are now allowed, there are also singular solutions, and they're still there. But in this case, the singular solutions is a bit more complicated. So you have the usual case. It should involve some 2s plus 1 string. Namely, you have the solutions that form an exact string, and it's from s to minus s, from is to minus is, and each root has difference I. But since repeated roots are allowed, you can have a more complicated situation, right? You can actually have say is repeated m0 times, is minus 1 repeated m1 times, and then yeah, all this can be repeated many times, and also the regular roots can be repeated many times. So then our situation becomes much more difficult. First of all, a priori it seems that we can take any values of this m0, m1 to m2s, but it turns out there are some constraints. So we'll talk about this later. So then first, what are the possible values of these multiplicities? And also, so in the spin 1/2 case, we derived the physicality condition for the singular solution, namely the condition which chooses the good solutions from the Bethe equations. But now we have many types of different singular solutions. For each choice of my m0 to m2s, I will have to impose some conditions. So what are these additional constraints for the regular roots? So this is also unclear. So this simple fact makes the analysis of the completeness problem, if we want to make analogy with the spin 1/2 case, much more difficult. So our strategy is that we want to first construct a Q system for the spin S case, and then we can show that it's complete both numerically and analytically. We want to first construct a Q system, and we want to show that it gives only physical solutions. And then in this way, we can derive the physicality conditions from the Q system. So the logic is a bit inverse in this case, because it turns out to be a bit easier. So now I will explain what is the rational Q system in the spin S case. So again, what is the difference? So the first difference is that the Young tableau is different. So previously in the spin 1/2 case, say here is the spin 1/2 case. If I take length so here I just give you one example. If I take length 2 and the 2 magnons, length 4 and the 2 magnons, so this gives a Young tableau of 2 rows. So the first is n, the second is L minus n. Now, if I change to spin 1, the Young tableau becomes this one. So the first row is still the magnon number, but the second row becomes longer. And also, the boundary condition changes. The upper boundary is always trivial, but the left boundary, especially this Q alpha, which is a Q00 I denoted before, it changes from spin 1/2 to spin 1. So here, notice I keep the length of the spin chain and the magnon number fixed. I just change the spin, and you see the Young tableau is changing. And also the initial condition, Q00, is changing. So what is the rule? The rule is that in general, for a spin S Bethe ansatz equation with length L and M magnons, the first row is still M, still has M boxes. And the second row has 2SL minus M boxes. So this is what is changed from the spin 1/2 case. Now, also the boundary condition is changed. So I will give you a general expression for Q alpha later. So then we talk about solving the Q system, right? Before, what we did was we first imposed the boundary conditions at the upper and the left boundaries, and then we solve the Q system. We require all the Q functions on the Young tableau are polynomials. So here we do the same, more or less the same, but there's one important difference is that we require this Q01 divided by alpha, where alpha is a polynomial, and the Q0b are the rest Qs to be polynomials. So remember, before we didn't distinguish Q01 and the rest of the Qs. So the question is, but we realize that in the higher spin case, if we don't do this, we don't get the correct solutions. So we need to require Q01 divided by alpha u, and the rest Q are polynomials. So the QQ relations are the same as before. So why is the first one special? Actually, we can prove that in the spin S case, we have the following result. So actually, this Q01 is related to the T function. So the T function in the TQ relation by this relation relation. So actually, requiring Q01 divided by alpha to be a polynomial is the same of requiring tau u to be a polynomial. So this is the main difference. And in the spin 1/2 case, this alpha is trivial. This alpha is just 1, so you don't see it. So that's why you don't distinguish the first node with the rest. Okay, and the minimality condition, which we see in the spin 1/2 case, is also changed a little bit. So previously we said the first 2 boxes are the minimality conditions. So in this case, in this higher spin case, we also have the minimality conditions. These are also 2 boxes, but these are the 2 boxes which are shaded green and blue. So the conclusion is that if we require that Q10 divided by alpha is a polynomial, then from Q02 and the Q0 to S, these boxes are automatically polynomial, if this guy is a polynomial. And if we require both these boxes, if we require both Q01 divided by alpha and the Q02S plus 1 are polynomials, then all the Q functions are polynomials. So the minimality condition actually becomes the polynomiality of Q01 divided by alpha and Q0 to S plus 1. So this is also the difference. And so how do we see that our proposal is correct? So we can check it numerically. So we check this result for for many cases. This is the result for spin 1 case, and we find the correct. So how do we check? We find the number of solutions are correct, are the one that is required by the completeness. And we also checked all the solutions that actually give you the good energy eigenvalue, and we compare it with a direct diagonalization. So this is some example for S equals to 1, and there's some example for S equals 3/2 and 2. And actually, there's we can also prove this more rigorously. And this, again, we need to use the polynomiality. So this is so again, we come back to this important intuition that the polynomiality is related to physicality. So again, let's come to the TQ relation in the higher spin case. So in this case, the TQ relation also, if you view it as an equation for Q, also has 2 solutions, the QU and the PU, which are the dual solutions. And the QU and PU, they satisfy the Wronskian relation, which is very similar to the spin 1/2 case, but the right-hand side is changed to this Q alpha. So remember, this Q alpha is what appears here. this Q alpha is what appears in our Q system. And for spin S, this Q alpha is given by this expression. And you see that when S equals 1/2, this is U to the power of L. This is we are back in the spin 1/2 case. So similarly, even if we require that tau U and the QU are polynomials, there is no guarantee that PU is a polynomial. In fact, we can show that by construction that the PU in general is not a polynomial when it has singular solutions. So this is situation, or this intuition is the same as in the spin 1/2 case. There you have the digamma function. Well, here you have a polygamma function. So it's a bit more complicated, but still the situation is the same, that P is in general not a polynomial. Now we prove that the dual solution PU is a polynomial if and only if Q01 divided by alpha and Q02 S plus 1 are polynomials. So this is a theorem proven in our paper. So remember that these two conditions are exactly our minimality condition for the rational Q system. So the conclusion is that our Q system, which we proposed, once again, is equivalent to the polynomiality of tau U, QU, and PU for the spin S TQ relation. And for this case, again, there's a nice theorem proven by Tarasov in a paper in 2008. So actually in this paper, only the result is given. So he gave a theorem, he gave the statement of the theorem, but he said this details of the proof will appear somewhere else, which we didn't find yet. But anyway, let's believe that Tarasov's proof is correct. Then basically he says his theorem proves the following thing. If both two solutions, QU and PU, to the TQ relation are polynomials, then the following result holds. First of all, tau U is an eigenvalue of the transfer matrix. So, and second, the corresponding eigenvector is unique up to proportionality. And the third is that the number of solutions is exactly the one required by completeness. So this means the conclusion is that if both QU and PU are polynomials, then again, the beta ansatz, this solution gives the physical solutions and all the good physical solutions. And since QU and PU are polynomials, it is equivalent to our Q system. So this proves that our Q system, rational Q system, actually gives all and only the physical solutions. And this is also backed up by our numerical checks. So this is the conclusion. And as we said before, now what we can do is that we can start from the Q system and see what kind of extra conditions we need to impose for the singular solutions. So for this is a bit, how to say, a little bit complicated to see. So it turns out that we can define this quantity, which we call BS. So it's made of this Q functions and this Q alpha, which we defined. And the additional constraint actually comes from BS, U is regular at U equals to 0, comes from this requirement. So why this is so, we also proved in our paper that this requirement, under the assumption that Q01 divided by alpha is a polynomial, is equivalent to the polynomiality of PU. Since polynomiality of PU is the crucial requirement in the Q system, so this is equivalent to the polynomiality of PU. So this is not completely obvious, but this is true. So from this BSU being regular at U equals to 0, we can derive the additional constraints. So let's see a few examples. So if we consider spin 1/2 case, namely the spin 1/2 solution, we consider the singular solution with plus minus I divided by 2 and the regular ones. Then the Q functions takes this form. And then we can plug in here using the Q alpha in the spin 1/2 case, which is u to the power of L. And you look at the expression, you require that this guy is regular at u equals to 0. You find the additional constraint, which is this curly Q. So the curly Q encodes all the regular roots. So the curly Q has to satisfy this constraint. And this is indeed what has been found before. Now we can also consider spin S singular solution where there's no repeated roots. So we just consider one exact string, and then the rest are regular solutions. So in this case, my Q function can be written in this form, where this curly Q again encodes all the regular solutions, all the regular roots. And you can require that our BS is regular at u equals to 0, and then you find this additional constraint. So this again confirms earlier results by Nepomniachtchi and collaborators. And we can even consider some strange solutions, namely a repeated singular. So in this case, we can take our function Q like this, and you can obtain the additional constraint from requiring BUS is regular at u equals to 0. But since here we have repeated roots, so it also has some other constraints from tau u being polynomial. So there's another constraint. Remember, we need to assume that Q01 divided by alpha is also a polynomial. So the conclusion is that if you give me a fixed set of number M0, M1 to M2S, and we can always derive the additional constraint for the regular guys by requiring that tau u is a polynomial, tau u is regular at u equals to 0, and also BSU, which we defined, is also regular at u equals to 0. But so far, there's one thing we didn't understand and didn't fully solve is that we still don't know what are the possible values for this M0 to M2S. A priori, it seems they can be arbitrary, but actually after some careful analysis, they are not. So we managed to derive some constraints for this M, which are the multiplicities of the singular roots. So I will just use this picture to try to finish this discussion. So we find that the allowed M's has to form certain pattern, namely they need to form this peak, and they are constrained. So you need to go up, and then you must immediately go down, and you can be flat, but there's no other possibilities. So this is one possible configuration for the multiplicities. So we would like to understand this part a bit better. So let me conclude. We propose the rational Q system for the spin S, XXX spin chain. And the Q system gives all and only physical solutions. So we check this numerically, and using Tarasov's theorem, we can also prove this rigorously. And we show that polynomiality of the Q function is actually equivalent to the polynomiality of the two solutions, namely PU and QU and PU of the TQ relations. And using our Q system, we can derive additional constraints for singular and strange solutions. So looking ahead, there are many directions we can pursue. So first, there's immediate generalization to Q deformations and the open boundaries and see if the situation is similar, and also to higher rank. And all these are under investigation. And second, we really want to understand what can be the multiplicities, the possible multiplicities, namely this M0 to M2S. So this we would like to understand better. And finally, we want to see, is there any applications of our findings? So we find these strange solutions. So there are some physical situations, say, can we observe this strange solution in the lab for some material? And this is also an interesting question. So with that, I will stop here. Thank you very much for your attention.
Thank you for very interesting talk. very interesting approach to the very old and in some sense classical systems. Okay, any questions, any comments, please? Dima, maybe you? Oh,
Yes.
okay.
Okay. So for the Q system, do the Q have some physical meaning? So you have this Q attached to the Yang tablet, yes. Does it have some physical meaning?
Yeah, I've been thinking about that. You mean all these Qs? So the only one which has some, say, meaning, or I'm not sure it's physical or not, has some meaning are some special guys. Like here, this Q is the Baxter polynomial, and this Q is related to the transfer matrix. So actually, each box you can rewrite it in a series of TQ relations in addition to this original TQ. But I don't see other, say, physical meaning of this Q functions so far. It would be nice to have some better interpretation for these guys. It seems at the moment it's like auxiliary function that we put in.
In fact, I had the same question. There are some discrete system like Tode system, which arise as some symmetries of, I know, of some statistical mechanical systems. So here, this auxiliary dynamics could have its own physical meaning.
Yeah, I do understand this question because this system exhibit a lot of similarity with the system people are familiar with. And in fact, Dima Volin and Christian Marboy, they invented this approach precisely because they studied the Y system and this Hirota dynamics in ADS-CFT. So here I just want to point out the difference is that, so for those kind of Q system, you have the symmetry for your system, and the symmetry gives you just one system, one Yang tableau. And now here, so it's I still have the same Heisenberg spin chain, but if I change the Magnum number, I need to change my Yang tableau. And also there's this minimality conditions. Actually, only two of them are really necessary. The rest, you can just throw them away. So actually, to formulate this thing, you don't really need the whole Q system. You can just take out the minimum guys, and it still works. So I'm not sure whether this Q system this Q function should have some very natural, nice interpretations or not, but I do hope they have.
Thank you. May I repeat my question about the relation with the cluster manifolds? So you said that this Q system is similar but not the same as such appeared in cluster algebras.
So I'm not familiar with cluster algebras. It just in this case, I never seen any connection or anyone mentioned this connection with cluster algebra. Maybe you're completely right. It just is my ignorance.
So there is some literature, for example, the paper of Di Francesca about Q system cluster structures related with such system. Okay.
Oh, that would be very interesting. So may I ask what do they use to do?
It's a big story, but principal object that the polynomiality condition in this subject could be the same as a Laurent phenomenon in cluster algebras.
Okay, then I should check. Maybe that will also give some hint for the physical meaning of these Q functions.
Yes.
Oh, that's very interesting. Thank you.
You probably know the subject of Bethe ansatz in the Gaden system. Gaden system quite a limit of the XXZ system. but anisotropic with different parameters on of interaction. In this model, the Bethe ansatz equation, so the Bethe condition in full generality, it means that in the case of coinciding roots, is covered by a quite general application of the G operas without monodromy. In a sense, so in fact, it is the same thing as the same condition as the polynomiality of the solutions.
I see.
Do you know the relation of this completeness problem with the Gaden one?
I think concerning the completeness problem, the meaning is the same. Namely, can you generate all the solutions? But is this related to my approach to the spin train? I'm not sure.
The analogous method of parameterizing such solutions in terms of these combinatorial tools?
Not as far as I know.
Okay.
But it's an interesting question. Maybe because Godin is some kind of limit of Heisenberg spin train.
Sure.
So in some simple cases, maybe one can try to take some limit and see whether we can use this approach to study also the Godin.
Thank you very much. Very interesting.
Thank you.
Dima,
I'm embarrassed that actually I'm not a mathematical guy, so I'm really just a physicist, and so I still need to learn quite something.
Yes. Dima, I think you can send the necessary references about cluster algebras to our speaker. Yes, you can find email on our site, and you can send. Oh, yes, I see your
yes.
reference in the chat. Thank you.
Yes, I can offer that.
Much.
Yes.
So, any questions? Any comments?
Right.
Okay.
Actually, I know Philip in person, and I know both authors, but I just didn't know their work in this direction.
Okay. So you can say thank you again. Very interesting talk. Thank you very much.
Thank you.
And the next seminar will be about Monge-Ampere system in and different applications. Thank you.
Thank you.
Bye.
Bye-bye.